All right, now we're going to start recording. If you're watching the recording later, you didn't miss much. You missed me forgetting to click record and a couple of people reminding me, and a brief description of the Fibonacci sequence and a description of the poster outside of G5 in the Rolla building. That's what you missed. So we're starting now to talk about the triangular numbers, which solve the relation tk equals tk minus 1 plus k, and t0 equals 0. So this is, of course, for k greater than or equal to 1. So we're to find a closed form for this, but first let's just list a few. So 0, and then t1 will be 0 plus 1, so that's 1. And then t2 will be 1 plus 2, so that's 3. And then 3 plus, I've lost count already. So t3 will be 3 plus 3 is 6. T4 will be 6 plus 4 is 10. T5 will be 10 plus 5, 15, 21, and so on. So, so these are called the triangular numbers. They're called the triangular numbers because they're the number of logs, if you will, in a triangular stack of the appropriate height. So if the height is 0, 0 logs. If the height is 1, 1 log. The height is 2, 3 logs, and so on. So how can we come up with a closed form for this? Well, tk equals tk minus 1 plus k, and t0 is 0. And so I'm going to unfold this recurrence, and I'm going to say, well, so long as k is big enough, tk equals, well, tk minus 1, but tk minus 1 is tk minus 2 plus k minus 1 plus k. And if I do that again, I get tk equals tk minus 3 plus k minus 2 plus k minus 1 plus k. And I'm going to do that until I have t0 plus 1 plus 2 and so on until I get up to k minus 1 and then k. And t0 is just t0 is just 0. So tk is equal to the sum as k goes from 0, not k, let's give it a different letter, I maybe, goes from 0 to k of I. Now we can just use the old baby Gauss formula, right? And that is going to be k plus 1 times k over 2. And then we can do a quick check back here. So this was t0, 1, 2, 3, 4, 5, 6. So t6 is 21. And 6 times 7 over 2 is 21, just to verify the formula. This kind of recurrence, a recurrence that can be written in the form sk minus sk minus 1 equals f of k. These are called, these are first order recurrences, but they're also first order difference equations. So this refers to the finite difference delta. I use partial difference notation, or you can think of it like partial derivative notation, because we very often in this class have sequences which depend on more than one integer variable. So delta with respect to k here is equal to, or sorry, of sk is equal to sk plus 1 minus sk, or in our case, we've written it the other way. We've written it as, this is called the forward difference, and this is called the backward difference, but they're just a shift of one another in terms of the sequence. So this equals is not really, but very close. And in the case of this particular thing, you can see that this would be f of k, this would be f of k plus 1. So that's why we can call them a first order difference equation. If I've got a relationship between k and k minus 1, then I also have a relationship between k plus 1 and k. So we could re-index this and make it a first order forward difference equation, or like I said, there is a backward difference. And there's also a, what do they call it? It's like a mid difference or the average. I can't recall what it's, but it's where you basically, it's s of k plus 1/2 minus s of k minus 1/2. Now that only works for some sequences that better approximate like a continuous function. Or I'm sorry, a function of like a real variable instead of an integer variable. So you don't have to worry about all of those. But recurrences in that form come from first order difference equations. And truthfully, even if it was a little bit more, if it was sk minus 2, sk minus 1 equals some g of k, we can consider that a first order difference equation too. It's just not as nice of one. So this one is a first order difference equation in the same way that f prime of x equals some expression for x was a first order differential equation in Calc 1. So the easiest kind, the kind you can get by integrating. And in fact, what we did here, because this guy was one, right? We can write him as tk minus 1 equals k. So that is a first order difference equation. And the way you solve a first order difference equation like this, where you have basically delta tk, or in this case delta tk minus 1 equals k, you solve this by summation. Summation is the discrete version of integration. So you would solve a simple f prime of x equals some g of x by saying f of x is an antiderivative of g. And when you have delta tk minus 1 equals k, then the sum of k equals tk in some way, shape, or form here. I'm fudging the notation. I'm not trying to show you exactly what to do, but we're going to sum this thing in order to figure out what our sequence was. But that's later. I like to get ahead of myself in this chapter because I really enjoyed difference equations. But I'm still just supposed to be telling you about them, not solving them, not showing you how to solve them. To a point, I can show you a few, but I'm not like teaching you the method to solve them right now, just showing you that some of the things that we've already done in other contexts can work. So let's see, example 4.4. We have the recurrence an equals 3an minus 1 plus 2 if n is greater than 1. And we have a1 equals 5. We're asked to find a5 plus a6. We probably could solve this whole recurrence, but we weren't asked to solve the whole recurrence. So if we just start with a1 equals 5, and we can just list these then. A2 then is 3 times 5 plus 2, so that's 17. Oops, not an equal sign. A3 then is 51 plus 2, which is 53. A4 is 53 times 3, which is 159, plus 2 is 161. This is maybe just at the outside of what I'd like to do without a calculator or without solving the recurrence. So then A5 is equal to 3 times 161, that's going to be 483. So I think that's 485. And then A6 is 3 times 485. Yep, I'm going to do that one. Hopefully I haven't made a mistake so far. Okay, I'm not reading it off my notes. I am doing that arithmetic in my head. So if I messed something up, I'm sorry. So 3 times 8 is 24, 25, 1455. So A6 is 1457. And you can just add them up. I'm not going to add them up. We found A5 and A6. Let's see. Can we come up with a solution for this? Probably not quite yet. I think I misspoke when I said that we could solve it. It's not as simple as the triangular numbers because of this 3 here. We're going to be able to solve recurrences like this, but I don't think we can yet. And I don't think I can just unfold it quite so easily. Example 4.5, I think we've done in another context. I think we did that when we were doing generating functions. Hang on a second here. I think I have that page. Yeah. So the generating function form for this is e to the 4x plus e to the 2 exponential generating function. E to the 4x plus e to the 2x over 2. So this is h of x. And so this is equal to the sum as k goes from 0 to infinity of 4 to the k plus 2 to the k over 2 times x to the k over k factorial. I'm not doing this quickly. This was in last time's lecture or the time before, I forget which. And so this is a k right here, 4 to the k plus 2 to the k over 2. So we already know what the solution, what this sequence is supposed to look like, but we can set up a recurrence for this sequence as well. So now I've set something down on top of my page. There we go. So code words from the alphabet 0, 1, 2, or 3 are recognized as legitimate if and only if they have an even number of zeros. So I'm going to use LK for the number of legitimate code words, length K, and I'm also going to define IK as the number of illegitimate code words of length K. I deal mainly in forward differences, so I'm actually gonna use these as is, and I'm gonna talk about, well, how do I make a legitimate code word of length k plus 1? Well, if I start with a legitimate code word of length k, and then I append to it a 1, 2, or 3, it doesn't change the number of zeros. So there are 3 things I can append to the end. So I start with my legitimate code word, and then I'm just going to add something to the end. Or I'll start with my illegitimate code word, and I'll add something to the end. And the number of, if I take an illegitimate code word and I tack a 0 onto the end, that forces it to be a legitimate code word. So the main issue is, what do I do with this? Because we don't want to have 2 sequences in our recurrence. But I left some room at the top of the page. What's the number of code words of length k, period? It's going to be, there's 4 choices, right? And there's k positions. So there's 4 to the k total code words, which means lk plus 1 equals 3lk. The number of illegitimate code words of length k is equal to 4 to the k minus lk. Right, a code word's either legitimate or not, and there's 4 to the k total. And so we can write this as lk plus 1 equals, that's going to be 2lk plus 4 to the k. And then we need our initial condition. We could say something about L0, but I think it makes the most sense to say L1 equals 3. Right, there's only 3 code words of length 1 that are legitimate. I think you can get away with this by saying that L0 equals 0. There are no legitimate code words of length 0. Or maybe it's 1. I guess it's 1. Yeah, and which is kind of odd, but I guess we're saying, well, that's the one with 0 zeros. That's an even number. But so that's maybe kind of dodgy. So let's say L1 equals 3. That's more straightforward. L0 equals 1 fits the recurrence. It doesn't necessarily fit the story because we're moving backward. And the story of the problem only really works for forward. All right, let's talk about derangements. I'm going to reorganize my examples here. This is something I probably do on the fly all the time, but a derangement is a permutation with no fixed points. Remember, a permutation like 1, 2, 3, 4 being shifted to 2, 1, 4, 3, that's a derangement, but 1, 2, 3, 4 being shifted to 1, 3, 2, 4 is not. So a derangement leaves no element in its original position. It's a permutation that leaves no element in its original position. So list all the derangements of 1, 2, 3, 4 was actually what I want to do next here. So if we start with 1, 2, 3, 4, then let's go through in order. So 1 cannot be here. So this could be a 2. And I could have 1 and then 4, 3. So this one exchanges the 1 and the 2, so I don't have any choices really about what I do with the rest. But if I put a 2 here and I don't put the 1 here, then I could put the 3 there. And then I could put the 1 here. Oh, I'm sorry, I can't put the 1 there because that would leave the 4 over here. So I have to do 4, 1. 2, 4, 1, 3. So I think those are all the derangements that start with a 2. Maybe not. Maybe. Yeah, I think that's it. So then what about a 3? Well, the easiest one is if I then replace the 3 with a 1, in which case this has to be 4 and that has to be 2. If I don't do that, if I say something like 3, 1, that leaves me with 4 and 2. So the 4 has to go there and the 2 has to go there. And if I say 3, put the 1 over there, that's the only place the 1 hasn't been yet, then I'm left with 2 and 4. So the 4 has to go here and the 2 has to go there. And so then if I start with the 4, I should get 3 of these, right? The easiest one is if I replace put the 1 in the 4's place, and then I have 3, 2 in the middle. But if I put the 1 here, then I've got 3 left, which has to go there, which puts 2 there. And if I put the 1 right here, which is the only place it hasn't been for the 4's, then the 2 is left, which has to go here, putting the 3 there. And I believe that there are only the 9 of them. I do not have that written down. I don't think. Let me double check. Yeah, I do. And it is 9. All right. So let's write a recurrence for this. And it's going to kind of follow what we were doing there. So I have a derangement of let's say n plus 1. So 1 can't go in its own slot, which means I have n choices of what to put here. And so if I say that I'm going to put k here, so k is one of the numbers between 2 and n plus 1. There are n choices for that. So if I say I put a k there, then there are 2 choices for how to proceed. The first is that then 1 goes to k. So we already have k moving to position 1. That's not normally the way we say that. Let me say it. We have 1 being filled with k, and so we could fill k with 1. And that's what I did on the first time for each of these, right? I said, well, if I put a 2 here, then let's put the 1 in the 2 spot. If I put a 3 here, let's put the 1 in the 3 slot. And if I put a 4 here, let's put the 1 in the 4 slot. So, and this is an OR argument. There are 2 choices and they come up with different things. And so this is a little bit like when we were trying to color C4 and we said, well, either these 2 are the same or they're not. And so we get a couple of choices. It's not the exact same argument, but it's a similar notion. So if we put the k into 1, and then we put the 1 into the k, then I just have n minus one things left. Sorry, I needed to define, we're going to say dn is the number of derangements of n items. So if I put the 1 into the k slot, after putting the k into the 1 slot, then I have d of n minus 1 ways to arrange the remaining n minus 1. And remember, there were n choices to get me here. So this, n times d n minus 1, is the number of ways that I can do option 1. If I put the 1 somewhere else, then how can I fill the remaining slots? Let's see. So if I put the 1, say I put the 1 here instead of over there. So now I have let's see. Oh, this is the same then as if the 1 and the k were the same number, in that the 1 I can kind of eliminate and put the k there, and now I have the question of how many ways can I derange n things. So that's not exactly what I did, but I'm just saying that if we treat the 1 and the k as the same, then this is really what's left to assign is 2 through n plus 1, not counting k, I'm not saying that right. Because I like to. It doesn't really matter. We could have started at dn. It makes the equation come out nicer. So let's see. The k goes here, and then the 1 has to go somewhere else. Oh, I know what it is. The 1 is not going in the k spot. That's the difference. And so there are n minus 1 places for the 1, but that's normal. That's exactly what 1 has. So I can treat this as though it is the 1 slot. And so then I just have this left to assign, which is the dn. Again, though, there were n choices before I got in here. So there were n choices, these n, for which one was my k. So dn plus 1 equals n times dn minus 1 plus dn. And this is the whole reason. If you don't have that, we can write it as dn equals n minus 1 dn plus dn, I'm sorry, that'd be minus 2, and dn minus 1. It's the same. Either way, this is a second order recurrence, so we're going to need, oh, terribly sorry. So dn plus 1 is n times dn minus 1 plus dn. Or if we hadn't shifted it to n plus 1 at the beginning, we get the same basic thing, just shifted down. We need initial conditions though. So there are 0 ways to derange one item. There's exactly 1 way to derange 2 items. And so that's enough initial conditions for us. Now we can use the formula and then kind of verify it. So D3, so that'd be 2 times 1 plus 0. That would be 2 ways to derange 3 items. And D4, that'd be 3 times 2 plus 1. That'd be 9 ways to derange 4 items. And 9 agrees with what we did. I think it fell on the floor on this page. And this agrees with what we did. So like I said here, K is 2, so then we put the 1 in the K slot. But if instead we put the 2 in here, then the 1, and we say the 1 doesn't go into the 2 spot, this is where we get, well, then it has to go in the 3 or the 4. It can't go in the 2, so we can treat it as though the 1 and the 2 are equivalent, and that's a derangement of 3 items here. There are 2 derangements of 3 items. And this is a derangement of 2 items. And that's what happened all the way down. Probably got time for example 4.9. A few of the things in the notes here, I'm just going to warn you, I don't think are things from our book. Like I said, I like difference equations and I like recurrences. And so at some point, and I skip these some of the time, and I believe theorem 410 is not from our book, but I'm going to double check before next class. If it is from our book, I'll go ahead and talk about it. But there's a good chance that I pulled it from a different book in just some semester I was teaching the class, in which case I'm not going to worry about it. That's also true if you're reading ahead at all. With example 412, a few of those are definitely methods that are not found in our book. I'll give you a reference for them when we get there. Let's see. Given a supply of $4 bills, $6 bills, and $10 bills, set up a recurrence to determine how many ways there are of giving n dollars in change. So let's define that as C of n is the number of ways to give n dollars in change. So if my change amount is exactly 4 more than a previous amount, then I add a $4 bill. Or if it's exactly $6 more than a previous change amount, I add a $6 bill. Or if it's exactly $10 more, I can add on a $10 bill. So if I could give change 8 ways for a previous amount for Cn minus 4, then I can give change that many ways just by tacking on a $4 bill and so on. The main issue with this one is the number of initial conditions I need. This is a 10th order recurrence. So I'm going to need 10 initial conditions. We might be able to get away with saying, sorry, not F, C of 0 equals 1. There's one way to give $0 and change. Don't do it. But you may not like that one, so we're just going to kind of put that in a box. How many ways can I give $1 and change? Yeah. Same for 2, 3, 5, 7, and 9, right? So then that leaves C4. There's exactly one way to give $4 and change. C of 6, there's one way to give $6 and change. C8, there's one way to give $8 and change. And C10. I have a 3 down here for C10. And I think that's because, yeah, order matters in this example. The original example, so we're counting it back by bill. And that's why we can say things like, well, I've already counted back so much, here's a 6, that puts us over. So that's a recurrence for this situation. And you've got to be careful. A lot of them are 0, but some of them are surprisingly large. I think I just said to write a recurrence, right? So that's our recurrence. Every recurrence we're going to do comes with at least one initial condition. So don't forget those when you're doing your homework, which I probably haven't assigned yet, but I'll get to that probably later today. Anybody have any questions before we get off here? All right, hearing none, I say this class meeting is adjourned. Make sure to email me if you guys find anything confusing in the project assignment.